Hi guys, today I want to discuss the topic nuclear force and binding energy. So as complicated as it may sound like, it's actually a pretty straightforward topic. This is one of the MCAT contents and it really intimidates a lot of students. So today I want to clear all the confusions you may have regarding this topic under just 10 minutes in just one page. All right, let's dive right in. So let's start with the very basic, okay, the structure of an atom. As you know, the nucleus has a proton and a neutron, right? Okay, and then this nucleus is also called a nucleon, as you may see on MCAT, okay? Nucleon, it just refers to the combination of neutron and proton. And then, of course, we have electrons orbiting around the nucleus. Okay, so there are two forces that's acting on the nucleus, okay? One is the strong nuclear force, okay? Okay, so why do we need this force? Because as we know, neutrons are neutral. They're not negatively charged that can be attracted to the positive protons. So this strong nuclear force basically binds the nucleons together, keep things together, okay? And then two is, I bet you know this force better. It's the electromagnetic force, okay? So here, the electromagnetic force is due to the electrostatic repulsion between the positively charged protons in the nucleus, okay? And then, as we know, if you want to make the atom stable, if the atom exists as a stable status, then the force 1 must be larger than force 2. So you have this net force that's keeping things together, right? Instead of being affected by the electromagnetic repulsion force that breaks things apart, okay? All right, so the atoms, so the particles in the nucleus stay together because force 1 is stronger than force 2. And then we have this net force, okay? All right, so if I were to break it apart, if I say I don't want it to be stable, I want the proton and neutron to exist on their own to do some research. So I'm gonna separate them, right? Okay, I'm gonna separate the nucleus. Then you must have to put energy to overcome the net force, right? That gets things together. Okay, so to give a name of this energy that it takes to separate the nucleus, it's called, as you may have guessed, binding energy. Okay? Or it's also called a nuclear binding energy, okay? So just to repeat myself, nuclear binding energy is the energy required to split an atom's nucleus into protons and neutrons, okay? We're gonna quantify the binding energy in just a minute, but now let's just do our experiment, okay? So let's say I have a helium atom, okay? I have 2 protons and 2 neutrons staying together, okay? And then I use some techniques, I separate them, okay? And then after I separate them, I have 4 individual particles. Then I'm gonna weigh them, okay? So this is my scale. So after I weigh the particles, I notice that when the particles are separated apart, they're heavier than when they were together, okay? And then this is really weird to me, right? Because according to the conservation of mass and energy, the total mass and energy before the reaction should equal to the total mass and energy after the reaction, right? So why is there this delta M, this difference in mass? Why is this delta M existing, right? Who's gonna make up for that, okay? So you can think about this way, okay? So because I have to break it apart, the nucleus, so I require some binding energy, right? I have to use some energy to make this happen. So this binding energy is actually what makes up for the heavier mass, okay? Since I used energy, I require an energy. It takes energy for this reaction to happen, okay? So I make it up by having heavier mass, okay? All right, so as you can tell, this is actually an endothermic reaction, right? And then the binding energy is always positive because the energy that you require to make this reaction happen as other endothermic reactions, in this case, the binding energy that you require is positive, whereas the exothermic reaction, remember when you learned the Gibbs free energy, delta G, when it's a negative delta G, then it will be exothermic, right? When you release energy, it's negative energy. When you require energy, when you need to use energy for this reaction to happen, then it's positive energy, okay? So nuclear bonding energy is always a positive number because it always takes energy to split apart the particles in the nucleus. All right, so not to confuse bonding energy with ionization energy, okay? Because ionization energy refers to the electron bonding energy. Basically, how much energy it takes for you to rip off one electron from the valence shell, right? Whereas here we're talking about the nucleus, okay? Different locations, guys, okay? So here we're talking about the nuclear bonding energy, not the electron bonding energy, which is ionization energy, okay? All right, so to quantify the bonding energy, we can use the famous Einstein's mass energy equivalence, which is the bonding energy equals to delta M times c squared. C is the speed of light, okay? Awesome, perfect. Now I think we can talk about a graph that you may see on a lot of websites. It's called a bonding energy curve, right? So it basically tells you, okay, which atom has the highest bonding energy. So here it is iron 56, right? Which means that it takes the most energy to split the nucleus, right? To break apart the nucleus into individual particles. AKA protons and neutrons. All right, so now let's move on to some applications, okay? So humans are really smart. Since we did this experiment that shows that, okay, this kind of going from high binding energy, I'll just use BE, okay, to low binding energy, it requires energy. Then what about we flip the reaction? We go from low binding energy reactants to high binding energy products. Then we will release energy, right? So we want to take advantage of this energy. So the application, we're going to learn two applications, and they're both based on the idea that we want the reactant to be low binding energy atoms and then go to the high binding energy products so that energy is released. It's exothermic reaction, right? Okay, perfect. So how do we do this? Let's just literally flip it, right? Two nucleus, and then we bind them together, right? That's how the sun works, right? It's called a fusion, right? That's the first application we're gonna learn. The sun works by fusion, right? The hydrogen atoms in the sun, they fuse to form helium, right? So that it generates energy on and on, right? Okay, perfect. So the second application is going from an unstable atom, right? The atom is not happy with the nucleus configuration of this atom. So the atom is anti. It wants to split into more stable atoms, right? The very famous example is the uranium gets split into, I believe it's barium and a krypton, right? Okay, and then in this case, energy will be released, right? It's also going from low binding energy reactants to high binding energy products, okay? So this is called a fission. Okay, so fission is basically it generates more neutrons, which goes on to split other uranium nucleus, and this is called a chain reaction, if you remember from your GenChem class. And then this is actually the mechanism of nuclear bomb, okay? All right, perfect. So that wraps up my video today, and then I hope it's helpful. I mean, it's not a super high yield MCAT topic, but it really intimidates a lot of students, and I hope since today you will have the confidence to solve all the topics on the MCAT regarding this. I hope that's helpful.